In this video, we're going to better understand how interest rates are determined in financial markets. That's chapter 4 of our textbook. In money and banking, the discount rate is a market rate of interest on a loan of some sort. We call it the yield to maturity. And for the equation below, the yield maturity is the red I. And we're talking about a coupon bond here. And a coupon bond has coupon payments, which for the most part are identical from period to period. And at the end of the coupon bond's maturity, you not only get the last coupon payment, but you also get a face value payment. The present value of this income stream over N years is the price of the bond. Again, F is the face value of the bond, or you can think of it as the future value. Price is the present value of those income payments. C is the coupon rate. Capital C is the dollar value of that annual coupon payment. If the bond states an annual coupon rate, then all you do is you take the coupon rate times the face value to get the coupon payment each period. N is the years to maturity. So down here we have a bunch of yield to maturities here, and we're assuming that the coupon rate is 10%, the face value is $1,000, and we have a 10-year bond. So face value is $1,000. Each of these 10 payments is $100, or 10% of $1,000. And then we replace the N here with 10 because this is in the 10th year. So if the yield to maturity is 7.13%, we add 7.13% to 1 and we get 1.0713 in each of these denominators. The first denominator is discounted one period. We raise it to the first power. 1.0713 raised to the first power is 1.0713. We have to discount this payment 2 periods. We have to discount this payment 3 periods. We have to discount this payment 10 periods. And because we also receive this in the 10th period, we have to discount it 10 periods. So the price of this 10% $1,000 10-year bond is the present value of this stream of payments. In Excel, we can calculate this using equal minus PV, parenthesis, the yield maturity with a percent symbol, the number of periods, the coupon payment, and the face value or future value. And when we do that, we get $1,200 when the yield maturity is 7.13. When the yield maturity is 8.48, notice that the denominators are all bigger, which makes each of these fractions smaller. So the price of the bond fell. If yield maturity is the same as the coupon payment, then the price of, or present value of this bond is the same as the face value. And notice the prices are falling as the yield maturities are rising. When the yield to maturity is 11.75%, the price of the bond is below the face value. You could say it's selling at a discount. When the yield maturity is even higher, it's even lower. The price of the bond is even lower. And notice every time we've changed the yield to maturity, the only thing that has changed in this Excel equation is the percentage. See that? The only thing that's changed is the percentage. We're holding everything else constant here. And as the yield maturity rises, the price of the bond falls. So if the yield maturity is currently 7.13, which is determined in the market, given these factors here, that bond would be priced at $1,200. We'd have to pay $1,200 for the right to get this stream of payments. If the yield maturity was 13.18 or 13.81%, to get these payments at that yield to maturity, we'd only have to pay $800. Now, suppose instead we hold, we know the prices of the bonds. We know the price of the bonds. How do we calculate the yield to maturity? Well, here we know the price of the bond, and we want to know what I is. Now, the problem with this is we can't solve this equation for I. We can only solve this equation for I if, say, the maturity was 1, 2, 3, maybe 4. If the yield maturity is 2, we could use the quadratic equation. If the yield maturity is 3, we could use the equivalent of a quadratic equation, but that's pretty big. It's like a half a page of formula. And if the yield maturity is 4, it would be about 2 or 3 pages if I remember right. So we have to use a numerical approximation to calculate the yield maturity here, which is all right since interest rates are usually reported in 2 decimal places. But we're going to use Excel. And the way we use Excel is we want to find the interest rate or yield to maturity. The yield to maturity is a rate. So we used equal rate with the number of periods equal 10. The size of the annual payments equal to 100. The price is in negative value because we have to pay this price to receive that annual payment and that final payment in year 10. So this to us is a payment out in order to get these payments that are inflows. That's why that's negative. And then this last thing could be either omitted in Excel or comma 0. And when we press enter after typing this into a cell in Excel, we get 7.13%. We change the price to 1100 and we get 8.48. We change the price to 1000 when the price or present value equals the future value, the yield maturity and the coupon rate are the same. And then we change it to 900 and we get 11.75. We change it to 800 and we get 13.81. So in either case, whether we know the price of the bond or we know the yield to maturity, as the price of the bond falls, the yield to maturity is rising. And that makes sense because the yield to maturity is in the denominators of all these fractions. How about a fixed payment loan? In a fixed payment loan, there is no balloon payment. There is the principal of the loan, which is the payment to the borrower after a loan is signed. Again, there is no balloon payment, so this face value is 0. So that this part here is just 0, and it disappears. And there are annual cash payments. I call it cash payment because of C here. But it could just be an annual payment, right? You could just pay it out of your checking account. So you call it an annual checking account payment, right? And then N is the years to maturity. And in this course, we're just going to assume that these are annual loans. So these are annual loans. They're not semi-annual bonds. We'll talk about that later. We'll complicate that issue a little later. For now, we're going to just think about things in terms of annual payments. Okay, so this example, suppose you buy $10,000 to buy a pickup. If you have to pay 60 monthly payments, well, I guess I'm wrong in assuming that we have just annual payments. So getting back to our example, if you borrow $10,000 to buy a pickup, if you have to pay 60 monthly payments of $200, what will be your interest rate? The thing you're looking for is the rate. So we're going to use the rate equation. So we're first going to do the monthly interest rate. So when we want to find the monthly interest rate on a loan, we type equal rate, and then 60 is the number of payments. 200 is the monthly payment, and then minus 10,000 to a bank, giving a person a $10,000 principal on the loan is a payment to someone. In exchange, the bank gets these inflows of $200 a month. So the $200 a month to the bank is an asset. It's getting these payments each month. But in order to do that, it had to give this person a $10,000 payment. So that's why that's negative. And then again, there's no balloon payment, so that is 0. And we end up getting 0.006183, or to turn that into an annual interest rate, we can use this equation, and we get 7.68%. But what we generally do in finance and banking is we just simply multiply this monthly rate by 12 periods, and we get 7.42%. So if we kind of use this you can think of as a simple average, and you can think of this as more like a geometric average. If we use this method, we get 7.68. If we just multiply by 12, we get 7.42. So they're kind of roughly the same. So when these values are small, the two methods produce roughly the same value. Okay, let's look at a perpetuity or a consul bond. A perpetuity or a consul bond has no end time. N is some really large number, right? It never ends. So you can think of it as infinity. So when you think of it, infinity is there's no end point to it. So what happens is I get a payment at the end of year 1. I get a payment at the end of year 2. I get a payment at the end of year 3. I get a payment at the end of year 4. I get a payment at the end of year 5. Yada yada. It never ends. So that's why it's called a perpetuity. Again, P is the price of this particular bond. It's the present value of the stream of payments. Whether there's a face value or not, it's so far into the future. Suppose there is a face value. It's so far into the future that by the time that face value is paid, you're going to be long gone. You're going to be deceased. You're going to be in the grave. So whether there's a face value or not, it doesn't matter mathematically, because it's so far into the future that F divided by 1 plus I raised to whatever that is in the future, that ratio ends up being really, really close to 0. So it could have a face value or not. Either way, this equation disregards it. So the face value is 0. And again, C is the dollar value of the annual payment. N is infinity, or the life of the government that issues the bond. Okay, now the interesting thing is we can rearrange this equation and actually solve it for I. So what I did here is I divided both sides by C, and then I just kind of rewrote what's left. So when I divide both sides by C, these C's are gone. I multiply this side by C, or sorry, I put parentheses around this, and I divide this side of the equation by C. I have to divide this side by C, and all these become 1s. So this is just 1 divided by 1 plus I. This is just 1 divided by 1 plus I squared, yada, 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 right? So these two equations are equivalent mathematically, as long as C is not 0, and C is not 0 here, because you're getting this payment every month or every year, right? So then I have this in a different color because I'm going to define this as X. So X is just 1 over 1 plus I. And because I is positive, 1 plus I is bigger than 1. So this value X here is between 0 and 1 for the most part. It's just between 0 and 1. And that's important mathematically. Okay, so now what I'm going to do is I'm going to add in a value of 0. Notice that the exponent starts at 1 here. I include x to the 0 because x to the 0 is 1. So 1 minus 1 is 0. So I'm adding in 1 here. It's a really popular technique in mathematical proofs. Okay, and the reason why I do that is because a series that starts with an exponent of 0 and goes to infinity, where this base is between 0 and 1, is said to converge. And it converges to 1 over 1 minus x. So this right here, from x to the 0 plus x to the 1 plus x to the 2 plus x to the 3, where x is between 0 and 1, actually converges to this value here. And then I can just use arithmetic to combine these two, right? This ends up being minus 1 plus x over 1 minus x. And then this minus 1 and this plus 1 is 0. And you just end up with x over 1 minus x. And then I just plug in back what x had equaled that, and I do a little bit more arithmetic, and I get something really simple. 1 over I, which is kind of amazing, right? So this here, all of this here is just 1 over I. All of that is just 1 over I there. And then I can rearrange, I can solve this for I, right? I can solve this for I. And when I solve this for I call it the current yield. The current yield is defined to be the current payment divided by the price of the bond, or the annual payment divided by the price of the bond. That's what we call the current yield. And for a perpetuity, the yield of maturity is the current yield. So here's our example. A console pays out $20 annually, and interest rates are 5%. Compute the price of the console. Well, this is pretty straightforward, right? You just plug in what you know. The coupon payment is $20 annually. The interest rate is 5% or 0.05, and then you solve it for P, and you get $400. A property that pays $150 annually and has a price of $2,500, all you do is plug in the value. So the current, the annual payment, cash payment is $150, and the price of the bond is $2,500. Well, then the current yield would be 6%. We can also do this in Excel. You might have to experiment with this 1,000. Sometimes 1,000 makes Excel, gives it a headache. So it's got to be a big number. So this is the number of periods. You can't obviously type in infinity, so you plug in some really big number, like something bigger than 200. So you plug in 200, and then this right here is the price, and then this right here is the, this is the annual cash payment, and this is the price. We pay this to get that, which is why that's negative and this is positive, and you get 6%. Now, if you get an error when you do this in Excel, then change this to something like 200, right? It's a numerical issue with Excel, a programming issue, if you will. Okay, now what about a zero coupon bond? A zero coupon bond is one where there is no coupon payment, right? So the coupon payment is 0 because the coupon rate is 0%. And so all these things fall out, and the only thing you're left with is this last summand. And we can solve this for I. We can actually solve this for I if we want to. And if we solve it for I, that involves, well, there's two ways you can do it. You can use logs. You could log both sides. Or you can just raise both sides to 1 over the nth power. And then it's pretty easy to solve it for I. So if you solve this for I, you get this. So this is a zero coupon payment or bond because the coupon rate is 0%. So you're not getting a coupon payment periodically. You're only getting the face value at the end of the bond. So here's an example. What is the interest rate of a $1,000 bond that matures in 9 years? We know this is a zero coupon bond because I don't give you the coupon rate. I don't give you the coupon payment, right? So all you do here is you're going to use either this equation or that equation because either you know the price or you know the yield to maturity. I'm going to give you the face value and the yield to maturity, but I may give you the yield to maturity or I may give you the price. So you either need to use this equation or this equation. We want to know the interest rate, so we're going to use this version of the equation. So we plug in what we know, and the price of the bond is $850, and the face value is 1,000, and it matures in 9 years, so that's why that's 9. And then you just plug that into a calculator, and you get that, or 1.822%. Now you could use Excel. So in a cell within Excel, you could type equal rate, because we want to know the interest rate or the yield to maturity. That right there is the maturity. 0 is the annual coupon payment or the periodic payment. The price is $850, so we have to pay out $850 to get $1,000 in the future. So that's why that's negative. So that's the future value, and this is the price, and we make that negative because we have to pay that to get that in 9 years. And you'd end up getting 1.822%. Okay, what about this one? If you require a minimum of 5% on a safe investment, what price are you willing to pay for a $1,000 bond that matures in 9 years? So now you want to use this version of the equation because you want to know the price. So you plug in your minimum return on a safe investment that you require here, 5%, and there's $1,000. That's 5%. You could also, well, I'll get to that when we go to Excel. And then you raised this sum down here, 1.05 to the 9th power. You divide that into 1,000 and you get $644.61. You could use the present value equation in Excel like we did earlier, because the price, if you remember, is just the present value of those coupon payments at a given interest rate. So we make it negative because if we don't make it negative, Excel's going to give us a negative number. So we use a negative there to reverse the negative symbol. And then the present value again is just the price when the interest rate is 5% of the $1,000 payment that you get in 9 years. So that's the number of years on this bond. The coupon payment is 0, the face value is 1,000, and the current interest rate, or the interest rate you need, is 5%. So the price would be, the maximum price you would pay for this bond is $644.61. Okay, what about a discount bond? A discount bond is generally considered a discount bond if the maturity is 1 period and there are no coupon payments. All you get is the face value, the value at the end of the period. So the number period is 1, and this could be a 30-day bond or a 30-day treasury bill, a 60-day treasury bill, or a 90-day treasury bill, or a 3-month treasury bill, right? All you get is the face value at the end of the period. And this is really easy to solve for I. It's just F divided by P minus 1, right? So here's the example. Compute the interest rate on a $1,000 bond that matures in just 1 year if it costs $850 today. So this is the price, and that's the future value, and it matures in a year or in a period. So the annual interest rate is 17.65% or 17.647%. You can use the rate equation in Excel by typing this into, like, for example, cell A1 of a worksheet in Excel. And we want to know the rate, so we use equal rate, parenthesis, 1 period, in this case 1 year. There's no coupon payment. You had to pay out $850 and you get $1,000. And you get the same thing. Okay, what about this example? 9 years after a bond was issued by the Treasury Department, compute the interest rate on a 10-year $1,000 bond. Now, when you buy it, there's only 1 year left. So you can think of this as a discount bond because you paid $850 today, and in 1 year you only get $1,000. So a bond like this that is bought and sold in the secondary market on the pages of the New York Times financial section is equivalent to a discount bond. It is in competition with a Treasury note that is 1 year in length and sold today and redeemed for $1,000 in 1 year. They're equivalent. Okay, so the way you do this is, I guess this is right. It's the same thing, right? Let me check here. What's going on here? $850 today, $1,000 in 1 year. Yeah. So there's no calculation to make here. It's the same as it was before. The price is $850. The future value is $1,000. You bought it a year ago, and then you're redeeming it this year for $1,000. So it's the same interest rate as that, right? Same exact. Use that equation, or use that equation. Okay. What price are you willing to pay for a $1,000 bond that matures in 1 year if you require 5% interest? You can either use this equation here, right? you get $1,000 in 1 year, and you require 5% at minimum, right? The maximum price you want to pay is $952.38, or you can use the Excel equation, where this is the rate, the minimum rate that you're willing to accept, 1 year period, 0 coupon payment, $1,000 face value, and we make the present value negative, and we get $952.38. How about a simple loan? Well, a simple loan is just like a discount, right? Where the principal is P, C is the cash payoff of the loan's principal and interest, and then N is 1 period, and it works just like it did before. If you borrow $200 and you agree to pay the lender $205 at the end of the month, what is the monthly interest rate? What is the annual interest rate? So if you borrow $200 today, and at the end of the month you have to pay that person back $205, then your monthly interest rate is 2.5%. Annually, that would be 30%. And again, that's an arithmetic average, and that's what we generally do in finance and money and banking. If you were to use probably a more accurate way to do this, a geometric average, it would be more like 34.5%, which is there's a big difference between 34.5% and 30%. Okay, some bond principles. The price of a bond falls if the yield maturity goes up. The return of a bond equals the yield to maturity only if it is held for n periods. And then under this situation, you have no interest rate risk. So if you buy and you hold it for all n periods, the return is the yield to maturity. Now, the return is not necessarily the yield to maturity if the bond is held less than n periods. Okay? So if a coupon bond is purchased and held for its final year, like going back to our 10-year bond that we bought in year 9, we're only holding it for the final year. So we get that final coupon payment and we get that face value. So this is like we bought it in year 9, at the end of year 9. We get to hold it for a year, and we get the face value at the end of the year. And this is year 10 of a 10-year bond, but we bought it in year 9. So that's kind of what's going on here. The return, if you will, we'll replace the I with return. And we solve this for R by just recognizing that both denominators are the same. So we can just simply add the numerators. And then we multiply both sides by 1 plus R. And then we divide both sides by P, and we get this. And then we can subtract 1 from both sides. And then we can just realize we can put this minus 1 into the numerator of the fraction by just doing this. We can multiply this by P over P, because P over P is 1, right? So we have minus P over P, and this whole expression on the right becomes that. And then we can separate here, right? This is equivalent to that. And this right here is interesting, right? This right here is pretty interesting. And this should be recognized as the current yield. This over here this is what we get at the end of the year, and this is what we had to pay at the beginning of the year to get that. So if it's a 0 coupon bond, the return is the capital gain of holding the bond for 1 year. That's what that is. That's this right here is the capital gain, right? So this is the current yield, and this is the capital gain. A gain is just a percent change in the value of the asset. So the price is what we paid at the end of year 9, and the face value is what we get when we redeem it or sell it back to Treasury, right? So this right here is called the gain, and this is called the current yield. So if it's a 0 coupon bond, then the return is just equal to the gain, the capital gain. If a coupon bond is purchased and held for its final year, and its purchase price equals its face value, then what can we do? We can just replace P with the face value. So if the price happens to be $1,000 and the face value is $1,000, then we can just substitute P with F, right? And then this part is gone, right? And so the return is the coupon payment divided by the face value. And if you remember what that is, that's the coupon rate, right? Because the coupon payment is equal to the coupon rate times F. And when the F's cancel, you're left with just the coupon rate. If a coupon bond is held for 1 year and sold before it matures, right? If we sell before it matures, then we replace the face value with that future price, right? This future price and the face value might not be equal to each other, right? So this is some future period. T plus 1 is some future period, right? And then we bought it today. So if we buy it today and we sell it before it matures at some future period, then this is not necessarily the face value, right? And so you can think of this as the gain where the future price is not equal to the face value, right? If a zero coupon bond is held for 1 year and sold before it matures, again, it's just the gain, right? If a coupon bond is held for 1 year and sold before it matures for the same price it was purchased for, then you only get the current yield. The return is the current yield. Okay, a rise in interest rates is associated with a fall in bond prices, resulting in a capital loss if time to maturity is longer than the holding period. The more distant a bond's maturity, the greater the size of the percentage price change associated with an interest rate change. The more distant a bond's maturity, the lower the rate of return results in an increase in interest rates. Even if a bond has a substantial initial interest rate, its return can be negative if interest rates rise. So here's an example. Going back to our example with 10% coupon payment of face value of $1,000, and this time we're just going to use 5 years. So we have all 5 summands right here. We have 1, 2, 3, 4, 5. And then in the 5th period, we also get the face value. So then we plug in the coupon payments, 10% of 1,000, and then we place F with $1,000. And then if the current yield is 10%, the price of that bond is $1,000, correct? Now suppose the current yield rises to 20%. Suppose the current yield rises from 10% to 20%. The price of that bond is $740. So this is what we paid in the past, right? Suppose we paid $1,000 in the past when the current yield was 10%. And interest rates rise to 20%. And we want to sell it today. Well, if we sold it today, the price would only be $741. So the capital gain would actually be a capital loss of a negative 25.9%, right? The current yield is 10%, and the return would be a negative 15.9%. So the increase in interest rates from 10% to 20% pushes the price that we paid initially from $1,000 down to $741, resulting in a return on this bond of a negative 15.9%. Because the gain is much more negative than the current yield. Prices and returns for long-term bonds are more volatile than for those for shorter-term bonds. And that's where we get the interest rate risk. And that's Chapter 5.